All right, so this lecture goes over relative velocity, and this is going to be kind of the end of our 2D motion chapter here. The lecture is going to be split up into two parts, though. In the first part, we're going to talk just plainly about relative velocity, and in the second part, will be a different lecture, and we'll talk about an example, a specific example involving a river, and 2D motion with relative velocity. All right, so we'll start with just 1D motion with this lecture. When we say something is moving relative to something, we like to think of whatever that something is that it's moving relative to. The something is thought of as having a velocity of 0. So if I am moving relative to the Earth at 5 meters per second to the right, we think of the Earth as not moving. But we know that's not true because the Earth is actually spinning and at the same time moving around the sun, right? So yeah, so whatever we say it's moving relative to, we assume that that something has a velocity of 0. So here's another example. If I am driving in a car going 25 miles per hour east, then the velocity of the car relative to the ground would be 25 miles per hour east, or written as positive 25 miles per hour, where we're assuming that positive is east and negative is west. When this happens, right, you could draw a picture if you like. There is, and the car is moving at 25 miles per hour east, and there's a person, say, standing here watching the car go by, right? This person would see that car is moving 25 miles per hour to the east, right? And so this is the velocity of the car relative to the ground. And the ground is where that person is standing, right? As somebody drives by in the car. I don't know why they're not smiling, but yeah, that was just, I don't know. I didn't have enough room for a smiley face. All right. While at the same time, the velocity of the ground relative to the car. So this, when we say the ground moving relative to the car, now we think about somebody maybe in the passenger seat. So maybe this person in the car that's not happy is the passenger, and they aren't driving, but because they're not driving, they're able to look outside at the ground. You know, and you've probably done this when you've written in the car and you're not driving and you look out the window and you see the ground moving, right? And you're like, whoa, the ground's moving. The ground, though, if you think of yourself as being stationary, right? So how fast is that ground moving relative to the car or relative to you that's a passenger in the car? You would say the ground is moving at 25 miles per hour west, or negative 25 miles per hour. All right. So this is kind of what we're doing here. Now, sometimes this is obvious to me, obvious to students that when we make these calculations, but sometimes it's not as obvious, and it's super tricky for some students. So let me just highlight this real quick. So and so how do we deal with this, right? So the we have a fallback, right? Like if you can't figure it out, if you can't see it easily in your mind, use the formula, use the math to help you out. And so what we have is a formula that I kind of refer to sometimes as the sandwich formula. And what it says is the velocity of object A relative to C. So this is read right here as the velocity of object A. Let me write that over. Relative to object C. is equal to the velocity of A relative to object B plus the velocity of B relative to object C. So I call this the sandwich formula because this new variable B gets sandwiched in between the old variables, right, which are A and C, like that. So this is the fallback when it doesn't easily make sense or you can't see the answer easily. All right, so I think an example will really help solidify how this formula works. So let's look at one right here. This is, it says a person is walking to the west at 2 meters per second on a train. So I'm going to go ahead and draw this, and I think that will help make it a little easier to see. So I'll just draw the boxcar of the train. Okay. I don't know. This is how my train looks. I don't know. Okay. All right. It works. It's good enough. And draw some tracks. Okay. So it says this person is walking to the west at 2 meters per second on a train. The train is moving at 9 meters per second to the east. All right. So here's the velocity of the train relative to the ground. Meaning if you, and we'll call east positive. Let's go ahead and label that up here. And we'll call west negative. So if you were watching this train go past, and let's say you were standing right here, and if that was the case, you would see, right, this is observer, but we can think of the observer as being the ground, right? That if you're watching this train go past, you see the train moving at 9 meters per second to the east. And so this is the velocity of the train relative to the ground, right? Where that observer is. It's just, observer is just stationary, a person just standing there on the ground. Okay, so, but then there's this person that is on the train walking to the west at 2 meters per second. So we'll say, since it's west, we'll say negative 2 meters per second. And this is the velocity of the person relative to the train, right? So we'll say, yeah, I'll just call it that. I'll say velocity of the person relative to the train. So the person is the person on the train, and the observer is on the ground. So we're calling one the person and one the observer, so we can keep the two separate. Hopefully that makes sense. All right, and then the question is, how fast is this person on the train, right? Assuming there's there's windows on the train or whatever. How fast is this person moving relative to the ground? So you might say, well, if I was standing there watching this, and this train passed, and this person was walking to the left at 2 meters per second, but the train's moving to the right at 9, then it would make sense to me that the person is still moving to the right, albeit at a slower speed, maybe at 7 meters per second, right? Because 9 minus 2 is 7, all right? And that's correct. So the person on the train has a velocity relative to the ground of 7 meters per second to the right. Now, if you can't see this, this is where like I said, the formula helps out, right? So let's just go ahead and write the formula, and I think it'd be best to just write out what the formula was again, and that was the velocity of object A relative to C is equal to the velocity of object A relative to B plus the velocity of B relative to C. And we sandwiched in this new variable B in between our old variables A and C. All right, but let's write it in words now, right? So we can say then, we can write it one more time. I'm just going to go ahead and put some lines here. So then we would have the velocity of the person, which is on the train, right, relative to the ground, is equal to, now we got to have a third object. And so what's that third object going to be? Well, we have the person, we have the ground. Ground is the same as the observer. So really the third object's got to be the train. All right, so we're going to say then the velocity of the person relative to the train itself plus the velocity of the train, because that's our object B, right? So it's going to happen twice right there in the middle of the sandwich, relative to the ground, because that's variable C. So I'm just following the formula, right? That's where this is coming from. Hopefully this is kind of obvious to you. And so A and C, person and ground, right? A goes here, C goes here, person goes here, ground goes here. All right, that's all I'm doing. All right, so therefore in numbers, this formula is written what? Well, we want to know what is the velocity of the person relative to the ground. Right? I think our guess was 7 meters per second to the right. Right, that's our guess. I can just write it up here. Guess is positive 7 meters per second to the east, right? Or 7 meters per second to the east. Okay. Okay. So I'll just write or 7 meters per second east. Okay. What is the velocity of the person relative to the train? So if there was another person on this train, and maybe that was you, and you were just sitting on the train, and you saw this person walking past you, going 2 meters per second to the west, you would just say, well, their velocity is 2 meters per second. You wouldn't care that the train's moving. You wouldn't care that you're moving. You wouldn't think about that, right? You'd just be like, oh, that person's just walking backwards at 2 meters per second, right? Because you're just sitting there on the train, right? And you see this person go by, and you're like, oh yeah, that person's just walking backwards at 2 meters per second to the back of the train. All right, so we're going to say then the velocity of the person relative to the train is negative 2 meters per second. And then what is the velocity of the train relative to the ground? Well, this is just if you're the observer now, right, the ground, and you can't see into the train, right? You just see this train going by. You'd be like, oh yeah, that train's going past at 9 meters per second, right? You would just be like, yeah, it's just passing by. I don't know if there's any people on it or whatever, but it's moving at 9 meters per second to the east. So the velocity of the train relative to the ground, the train's moving at 9 meters per second east, or positive 9. So what we have then is, if we do the math here, we see that the velocity of the person relative to the ground is going to equal positive 7 meters per second, or 7 meters per second east. All right. So hopefully this is making some sense. And now you kind of see how the formula backs up what we could intuitively see. So use the formula when it's necessary. Sometimes it can be harder than the problem itself. So that's why I say don't worry about the formula too much. It's there when you need it. Okay, let's go ahead and try some of these examples. All right, so in this case, I'm going to go ahead and draw this down here. And what's going to happen here is we're going to have a car. We'll say it's car. I can't draw with this stupid. Why is that? Okay. So let's say we have a car that is, we'll call it car A. All right, and car A is going to be going 50 miles per hour to the north. And I'll just write that down right here. And we'll call north positive. Let me write it over here. And we'll have it point that way, and south will be negative and point that way. All right. And I'm just going to, just because it makes this problem a little easier, I think, I'm going to draw car B in front of car A. And car B is just going to be kind of pulling away, right? It's going to be traveling a little faster. And maybe this is on the expressway, so it's still a safe speed. But car B is traveling at 70 miles per hour. Make that vector a little longer for B. And yeah, okay. So that's kind of what we have. And maybe I can even add a little color there, some green highlighting to B. All right. And A will be yellow. Okay, so this is what we have happening, right? Both cars are heading north, and it's good. All right, so then they ask us some questions. Car A drives 50 miles per hour to the north. What is the velocity of car A relative to the ground? All right, so the ground would just be a person standing over here, watching safely from a distance, watching these cars go past, and this person would be like, that car is going 50 miles per hour to the north, right? And because that's what they would see. This is the velocity of car A relative to the ground, right? It's very, the ground isn't moving, the person isn't moving, so we can just say that this is going to be positive 50 miles per hour or 50 miles per hour north. All right. Then the next question says, what is the velocity of the ground relative to car A? So if you were a passenger in car A and you look down at the ground, you would say, well, the car is not moving, right? Since I'm in the car and I'm not moving, right? And I look down at the ground's just whipping backwards and moving backwards at negative 50 miles per hour or 50 miles per hour south. All right, good. Then the next question says, car B drives 70 miles per hour to the north. What is the velocity of car B relative to the ground? All right, so this is pretty much the same as question A was, but for a different car. So this time it's going to be 70 miles per hour positive or 70 miles per hour north. And what is the velocity of the ground relative to car B? Once again, if you were a passenger in car B and you look down at the ground would be moving backwards at 70 miles per hour in the negative direction, or we could say 70 miles per hour south. And then what is the velocity of car A relative to B? So now we want to know VA, comma B, but we need a third object, right? And so that third object can be the ground, right? And that'll be that observer. So let's go ahead and write this out. Velocity of A relative to the ground plus the velocity of the ground relative to B. All right, so good. So we got our third object in there in our formula, and we should be good figuring this out. So therefore, in numbers, what would this be, right? So we have the velocity of car A relative to B is equal to the velocity of car A relative to the ground. So car A is moving 50. It's the slower car. And relative to the ground, we said it was positive 50. So this is going to be our positive 50 right here, miles per hour. And we are going to add that to the velocity of the ground moving relative to B, Well, we said that B was moving positive 70 relative to the ground, but the ground relative to B was negative 70. So we can do the math there. Positive 50 plus negative 70 is going to equal negative 20. And maybe we should have just guessed, first what this was really saying, right? And my point is this. All right. The question initially asked, what is the velocity of car A relative to B? So if you were in car A and you were watching this happen, you would see this car that's traveling faster in front of you just kind of moving away from you, like the distance between the cars getting larger and larger. But the car wouldn't be going away from you like crazy fast, right? It wouldn't be going away from you at 70. No, it'd be going away from you at like 20, right? But this is asking the opposite. Ooh. All right. Let me start over with that again. Let me try that one more time because I think I said that the other way. So this says the velocity of A relative to B. So since it's relative to B, you are a passenger in car B. So you are watching the same thing play out as a passenger in B. All right. So as a passenger in B, you are gradually pulling away from A. But remember, if you're in car B and you're the passenger, then you're not moving. So what you see is car A just drifting off into the sunset, right? Just drifting off behind you further and further away. So it would appear that they are moving backwards, not at 50 miles per hour, but at a slower speed, maybe 20 miles per hour, drifting backwards, right? Backwards at 20 miles per hour, moving south at 20 miles per hour, negative 20 miles per hour backwards. And so that's what we see. All right. The opposite happens in the next part where it says, what is the velocity of car B relative to A? And this is the scenario I started to explain. So what is the velocity of B relative to A? We would say, well, if we were sitting in car A, car B just appears to just be gradually increasing its distance away. Not increasing it away at 70, but just pulling away from it gradually until it's out of sight. And so we would say that it's moving away slowly north at, because we're a passenger in A, right? This is relative to A, right? Velocity of B relative to A. It appears to be pulling away to the north at positive 20. So see how that works? If I go back up and we find a highlighter here, velocity of A relative to B was negative 20, and then the velocity of B relative to A is positive 20. So let's go ahead and prove this really quick with the sandwich formula and see that our guess, right? This was our guess. It's right, but I just want to go through it really quick. So we have the velocity of B relative to A is equal to the velocity of B relative to the ground plus the velocity of the ground relative to A. So I'm going to go ahead and put some numbers in there. What is the velocity of B relative to the ground? That was the positive 70 miles per hour, right? Because that's how B is the faster moving car. And what is the velocity of the ground relative to A? Well, if you're in car A, which is a slower car, you would be like, oh yeah, look down at the ground. The ground's moving away at 20 miles per hour to the south. So, 50 miles per hour to the south. And so this would be our negative 50 miles per hour. So we add the two together, 70 plus negative 50 is positive 20 miles per hour, or 20 miles per hour north. This is the velocity of B relative to A. Go ahead and put a red line around that if you like. Okay. All right. So far so good. Let's go ahead and look at this next problem. We're actually going to save this for 2D motion for the next lecture. And we're going to go to, this should be under relative velocity practice right here. So if you want to open up this worksheet, so you have this one, you can. If you're just writing this down on a separate sheet of paper, then no big deal. We're going to work through 7 through 10 together. All right, so number 7 here, it says a river has a current of 6 meters per second. All right, so I'm going to just go ahead and draw this, maybe draw it right here. So if this river was passing by, we would say, and we'll call right positive and left negative. And sure, and if we want to call them east and west, we can, but this will be good enough for right now. And we'll say that this river is moving at a positive 6 meters per second. And this is really the velocity of the river relative to the ground. Right? That's really what that's saying. It's moving to the right at positive 6. If you were on the ground watching this river go past, you would be like, yeah, that river is definitely moving right at positive 6. Okay. Then it says, if a boat can travel 20 meters per second in still water, then its speed relative to the shore is what? Okay, so, and then it says, when going downstream or when going upstream. So if the boat is traveling a speed relative to the water, right? What we're saying is the velocity of the boat, I'm trying to think of how best to say this. The velocity of the boat relative to the water, so VB water, is equal to 20 meters per second. And it depends on how we point that 20 though, right? So meaning, if this is the boat right here, if it's pointed to the right, then we're just gonna, and we see this boat go by, then obviously this boat's gonna be traveling faster than 20, right? The velocity of the boat relative to the ground, which is what the problem is asking. And I should probably be careful here about my different words that I'm using here, because I want to keep it just three words, right? So I'll spell out boat, and we'll call this river. So this is the velocity of the boat relative to the river. Regardless of whatever way it's pointed, it's going to be 20 in magnitude. The sign is going to be different based on where it's pointed. So if we wanted to know, say, the velocity of the boat relative to the ground, like if you were on shore watching this, you would say, oh, well, that boat relative to the ground would be moving at 26, right? And we could say positive, right, where that's to the right. And if the boat flipped and went the other way, then the velocity, if the velocity of the boat relative to the river was in this direction at negative 20 meters per second, we would say, well, the river's fighting it, right? Because it's going upstream now, or against the current. And then we would say, well, it's going slower. We were watching this boat now go past. We would be like, the boat relative to the ground is negative 20 plus 6, so negative 14. It's still going in the negative direction, but it's not going as fast as it would if there was no current. And yeah, so it's definitely going slower than it would be without a current. Okay, so can our formulas help here? You know, and the answer is yes, right? So if this doesn't make sense, or if you're not seeing it, for the first part, if we said, what is the velocity of the boat relative to the ground, you would say, well, what's the velocity of the boat relative to the river plus the velocity of the river relative to the ground. And we'll have this first example be, we'll have it be when the boat is going downstream. Right, so this would be our guess was 26, right, for this one. So I'll write that in parentheses here. We think it's going to be 26, right? To the right. Okay, so the sandwich formula that I just used there, hopefully that makes sense, right? It was VAC is equal to VAB plus VBC. All right, so my three objects there. You can see that I sandwiched in, for object B, I used the river as my third object. Okay, and all right, so I think we're ready. So what is the velocity of the boat relative to the river? Well, the boat relative to the river is what it does normally when the river just isn't doing squat, right? And it's just going to be its normal speed of 20 meters per second. All right, but since the boat is pointed to the right, we're going to call this a positive 20. And we're going to add that to the velocity of the river relative to the ground. Well, if you're on the ground watching this river go past, we are seeing something along the lines of this being positive 6 meters per second. So 20 plus 6 is just going to be positive 26 meters per second. So once again, the situation we were working with here was not this one over here, right? But this one right here. So that when this happens, this is our sandwich formula backing this up. The opposite situation would be proven by the sandwich formula. If I use this extra sheet of paper I have here, the opposite situation would be like this. Let's go ahead and draw this boat. But now I don't know why my boat looks, because I could draw it kind of pointed, right? It might look better. This is terrible. I'll just stick with this. That's about as good as it's going to get today. Can I draw a windshield? That's not bad. Yeah, that's right. All right. So you got this boat, and it's going upstream now because you got the river still going this way. This is the velocity of the river relative to the ground. It's going to still equal positive 6 meters per second. And you got the velocity of the boat relative to the water. Let's see, let's go back to black. Is going to be and we're calling it the river, not the water, is going to equal negative 20 meters per second. And we want to know what the observer would see, right? Or what is the velocity of the boat relative to the observer, or the boat relative to the shore, right? And I think we called it the ground. So we said VB ground, right? And we predicted negative 14 meters per second. So here I'm saying sandwich formula, VAC equals VAB plus VBC. Velocity of the boat relative to the ground is equal to the velocity of the boat, our third object, is going to be the river, relative to the river, plus the velocity of the river relative to the ground. So we just sandwiched in that new variable, right? For variable b is the river right there. Okay. And so I can go ahead and write it out one more time. So if you saw this boat going past, we predicted, I think it was 14, negative 14 is what we predicted. Let's see if that's true. The velocity of the boat relative to the river is going to be, we have it written up there, right? It's moving. The boat would go, if the river wasn't moving, it would just go negative 20 because it's going to the left now. It's going upstream. So we're calling left negative. Just make a note of that up here. Right, positive. And then we are going to add that to the velocity of the river relative to the ground. Now, if you're watching the river go past, it's still going 6 to the right. So this is going to be positive 6 meters per second. Negative 20 plus 6 is negative 14 meters per second, just like we predicted. All right, so you can, all right, VBG or VB ground. Okay, and there you have it right there. So formula backs up what I think is obvious, and I don't expect you to use it, but I just want to go through it so you understand that whenever it doesn't make sense, fall back on the formula to help you. Okay, this next one. Two moving sidewalks. Sidewalk A and B are next to each other in the airport. All right, so what this looks like is kind of like this. You have this sidewalk A, we'll call it SA, and it's moving to the right at positive 2 meters per second. So this is the velocity of sidewalk A relative to the ground, right? Ground, maybe there's an observer right here watching this the sidewalk go past. Where do they have these moving sidewalks? At airports, because people don't like to walk with their luggage. And then sidewalk B is moving to the left at negative 2 meters per second. So at airports, kids like to play on these sidewalks, and yeah, because it's fun, right? So let's go up here and look at these. So Alex is sitting on sidewalk A. It says Alex is on sidewalk A and is sitting on the ground eating a granola bar. All right, so that's kind of confusing. What it's really saying is Alex is on sidewalk A and is sitting eating a granola bar. Let's get rid of that on the ground part. That makes it sound like he's not on the sidewalk. No, he's on sidewalk A and is sitting eating a granola bar. What is his speed relative to a stationary observer? So this is asking us, what is the velocity of sidewalk A relative to the ground, right? And because Alex is just sitting on sidewalk A, so we know when we just said this, right, because it was kind of obvious, we said the velocity of sidewalk A relative to the observer is going to be positive 2 meters per second. Okay. And where we're calling to the right positive and we're calling left negative. Okay. And that's all based off of how we drew these two sidewalks. They didn't tell us which direction. They just kind of told us they were going opposite directions. All right, so we're calling right positive, left negative, and we define sidewalk A as moving to the right down there with our drawing. Carter runs along sidewalk A at 10 meters per second. All right, so Carter, if we see Carter go past, if we're the observer sitting here or standing on the ground, and we see Carter running on sidewalk A, right? If he is running at, so velocity of Carter relative to sidewalk A is going to equal 10 meters per second. So we see Carter running at 10 meters per second on the sidewalk, and we are standing there on the ground. Then Carter is going to be moving at what speed relative to the ground? Well, we would see him moving we have the positive 10 plus the 2 of the sidewalk, right? So we would see Carter moving even faster. So we would see the velocity of Carter relative to the ground is going to equal positive 12. And if that doesn't make sense and you want to use your formula to kind of see that, here's what you could do. You could say, let's see, how do I best write this? We could write velocity of A relative to C is equal to the velocity of A relative to B plus the velocity of B relative to C. All right, so we have velocity of Carter relative to the ground, which is what we want to know, is equal to the velocity of Carter relative to sidewalk A, right? We got to have another object, plus velocity of sidewalk A relative to the ground. Okay. So V Carter relative to the ground then is equal to Carter relative to sidewalk A. Carter's going to be doing his positive 10, right? And sidewalk A relative to the ground, which is what we found in the first part, right? I think that was what we saw for, yeah, in number 8 was the 2 meters per second in the positive direction. All right, so we can see positive 10 plus 2 is just going to equal positive 12 meters per second, or 12 meters per second to the right. All right, and this is our answer for number 9. Okay, and there we go. Proof of what we guessed, right? Or maybe just knew, but proof once again with the formula when we need it. Okay, and then finally for number 10, if Evan runs against sidewalk A and his speed on regular ground is 8 meters per second. Now, not relative to the ground. It's not saying that. It's saying his speed on regular ground, speed, no direction, just saying, he normally, when he runs normal, he's running at 8 meters per second. So then he gets on sidewalk A, runs in the opposite direction against sidewalk A at 8 meters per second. And since it's against sidewalk A was our positive sidewalk. So this is against it. So we're saying he's going to have, we're saying V Evan relative to sidewalk A is going to equal negative 8 meters per second. So he's going to normally go, if sidewalk A wasn't moving, he'd be going 8 meters per second to the left. And that's against A because A goes right? Okay. How fast will he be running relative to a stationary observer not on any sidewalk? Okay. So, all right. This isn't as bad as I thought. I thought this was a tougher problem than it was. But, oh, I see. So I messed up on the last one. Okay, I didn't finish the last one is what happened. All right, so we never finished the last, because the last problem says, what is Carter's speed relative to someone standing on sidewalk B? Okay, so let's go back and get that first. So right now, we're only halfway through problem number 9. We know that Carter's speed relative to someone on the ground is positive 12 meters per second. But this isn't the answer. So let me just erase that, and I'll keep the box around this. We want to know what's Carter's speed relative to someone standing on sidewalk B. Let me draw that in black. Okay, so someone's standing on sidewalk B, and they're moving to the left at negative 2 meters per second. Then Carter is moving 12 meters per second to the right relative to someone on the ground. But how fast is Carter moving to somebody standing on sidewalk B? All right, so what this is asking then, or what this is saying, or what our prediction is, if you are this person, if this is you, and you saw Carter run by, if you saw Carter run by from here, if you were this person, you'd be like positive 12. But if this is you here on sidewalk B, and you're moving away from Carter, you might say, well, yeah, Carter's moving even faster than that, right? Because he appears to be moving at 2 meters per second faster than the 12, which would be 14 meters per second to the right. So that's our guess here for number 9, would be that Carter is moving at 14 meters per second relative to the right. So this doesn't answer the question. So I'm going to get rid of this for right now. And we want to know, what is velocity of Carter relative to sidewalk B? That's what we want to know. So our guess for this, and I'll just write this down, guess is positive 14. Okay. So coming back down here, this is still good. What we did is still good. We just have to add on to it a little bit more. So let me get another page here. Oh, I just lost something in there. V Carter relative to the ground. Yeah, I'll just rewrite that really quick. Okay. So what we want to know is, what is the velocity of Carter relative to sidewalk B? So we're going to go ahead and use the sandwich formula. And so you can see, if the third object is the ground, what we did previously is going to be useful. All right. So what we're saying then, let me erase this really quick. What we're saying then here is the velocity of Carter relative to sidewalk B is equal to the velocity of Carter relative to the ground, which is our positive 12 meters per second, right, from before. All right, so I just brought that down here, plus the velocity of the ground relative to sidewalk B. So what would that be? Ground relative to sidewalk B. Well, if you're on sidewalk B and you look down at the ground appears to be moving 2 meters per second to the right, because you're moving 2 meters per second to the left. So you look down, the ground is moving backwards at 2 meters per second, which backwards for you would be right because you're moving left. Okay, so this is going to be positive 2 meters per second. So my point here then is that the velocity of Carter relative to sidewalk B is just like we predicted, that faster velocity of 14 meters per second. All right, good. And there's our answer to number 9. Okay, so number 9 was tricky. And kind of like 2 problems in one. You might have been like, oh, well, I didn't need to do this part. I knew that Carter would be moving that faster velocity if he's running at 10 to the right and the sidewalk's moving 2 to the right. That obviously is Carter relative to the ground is positive 12. Good. Yeah. I mean, if you can see that and you don't need to write all this out, then by all means, that's fine. All right. Part 10, or number 10. If Evan runs against the sidewalk on A and his speed on regular ground is 8 meters per second, how fast will he be running relative to a stationary observer not on any sidewalk? So we want to know, what is the velocity of Evan relative to the ground? And when Evan runs relative to sidewalk A, he runs at 8 meters per second. And because he's running against the sidewalk, it's going to be running left at -8. Sidewalk A moves to the right at +2. So this formula is going to look like this. The velocity of Evan relative to the ground is equal to, what's our guess here? If we see Evan running 8 meters per second against the sidewalk, which is moving 2 meters per second the other way, and Evan's running left, so we would predict, well, he goes even slower, or he goes still left, but a little slower. So we would say our prediction is probably -6 meters per second, right? 6 to the left. All right, let's check that out and see if that's right. So the velocity of Evan relative to the ground is equal to the velocity of Evan relative to sidewalk A. That's going to be our third object. I'm going to write that E over. Plus the velocity of sidewalk A relative to the ground. All right, so V Evan relative to the ground is equal to V Evan relative to sidewalk A, which is that -8 meters per second, plus, sidewalk A relative to the ground moves at that +2. So we end up getting a -6 meters per second. All right, so hopefully, though I had to backtrack on that one problem, hopefully this is making some sense here. And once again, if you can see the answer without showing your work, good. If you ever can't see the answer, that sandwich formula is there to help and back you up on these problems. Whoops. All right, that's it. So next time we'll cover relative velocity in 2 dimensions.